apologies to those of you who are sitting near the speakers, because I can easily fill this room with the sound of my voice without this amplification. But they tell me that this is the only way it can be recorded. So I assume everyone can hear me? Sorry? Well, the little green light is on anyway, for what that's worth. OK. So I want to thank the organizers for inviting me out. I want to thank Christina for not saying how long ago it was that I did this work. And thank you all for coming at such an early hour. If it's any consolation, it's an hour earlier for me, although it might be actually 7 hours later because I was in London 3 days ago. Of course, Jean-Francois has had a rather harder time than that. Anyway, so what I want to tell you about today is a continuum theory of flocking. Don't be intimidated by the title. Don't be intimidated by the fact that I'm using transparencies. This talk is going to have 2 parts. The first part is intended to convince you that I solved this problem by deep flashes of intuition and inspiration, and that I'm a genius. That's the part that's going to be done with the computer. And then for the next 2 lectures, I'm going to be honest and tell you how we really did it. And the message I want you to take away from that is that you can really do this stuff by applying some techniques that I think pretty much anyone in this room could learn how to use. And they're powerful enough that you can do things that seem, if you just tell somebody about it, like magic. So that's what I'm going to tell you about. It's a continuum theory of flocking. The original idea that physicists might have something to say about flocking was due to Thomas Wiesek of the Jódfos Institute in Hungary. All the work I'm going to describe today, all the theoretical work I did in collaboration with Juhai Tu, who, much to my amazement, is still at IBM Research 20 years after we did this work. OK, so let's, I can do this. Great. And I should add that everybody who works on the field of works on birds owes a lot of their inspiration, of course, to Alfred Hitchcock. OK, so I want to be very precise about what I mean by flocking. So what I mean by flocking is any situation in which you have a large number of things that are self-propelled and that all move in the same direction. There's a few more bells and whistles that I'll get to in a few slides. Often, but not always, those things are living creatures. And so here's an example of, it's kind of hard to see this picture, but this is several 100,000 wildebeest moving across the Serengeti plain. A lot of people complain to me about this picture because you can't actually see the horns on the wildebeest. I think that's actually a plus, because the whole point of what I'm going to tell you about here is that the fact that the wildebeest have horns doesn't matter. Or more to the point, or more generally, all of the details about the behavior of the wildebeest don't matter. The only thing that's important is, there's 2 things that are important here. Well, 3 things that are important here. You didn't expect the Spanish Inquisition. OK, so there's 3 things that are important. The first thing is that this is an enormous herd. So this wildebeest over here, start again. This wildebeest over here cannot see that wildebeest over there. Yet they're both moving in the same direction. Okay. The second point is they're not doing that by cheating. They aren't all carrying compasses that tell them which way the waterhole is. All they're doing is following the wildebeest they can see, and the wildebeest they can see are just 4 or 5 or maybe a dozen at most in their immediate vicinity. Okay. Nonetheless, this entire collection of several 100,000 wildebeest are all moving in the same direction. Okay. So 2 points there. The interactions are short range, but the order is long ranged. And the second point is, why does this keep coming up? Agree? Where is agree? Go down, OK. Uh-oh. Oh, wait, here we go. What? And so this is an illustration of a point I wanted to make later, which is that I'm not a tech guy. OK. Full screen mode. Here we go. OK, now where am I? Don't watch for a minute. This will make you disoriented. OK, yeah. OK, so the first point is you've got long-range order here arising out of short-range interactions. The second point here is that the direction these creatures are picking to move is chosen by them. It's not imposed externally. Okay? The buzzword for that is this is, or the buzzwords is that this is a spontaneously broken symmetry. Okay? And the third point is that they're succeeding in doing this. Okay? One of the things I'm going to try to convince you in this talk is that what's going on here is actually astonishing. In fact, it's so astonishing that I abandoned my career as a conventional soft condensed matter physicist and started working on this problem because I was so baffled by it. So what I hope to do in this talk is convince you that you should be flabbergasted by this, not just because of its scale, but because it happens at all. And then I'll try to make you understand why it is possible and why it does happen. OK, the theory I'm going to describe works equally well in 2, 3, or if you like to do that sort of thing, 4 or more dimensions. So here's an example of flocking in 3 dimensions. It also comes from Africa, which is a bit discouraging. It makes you think that maybe Africa is the only place with collections of wild animals this large left in the world. This is also, it's about the same size as that wildebeest herd in terms of the number of creatures. There's several 100,000 flamingos, and again, they're all flying in the same direction, presumably not following a compass. OK, the most dramatic example of this that I know of, although some people are going to jump up and scream about this, but the thing that originally got VSEC interested in this was the observation that in bacterial colonies, you frequently see billions of bacteria all moving coherently. Okay, now, actually, further study of this has shown that this doesn't actually happen, but VSEC thought it did, and this got him interested in this problem. OK, so what do I mean by flocking? So what I mean is a situation in which moving organisms spontaneously break a continuous symmetry. In this case, the continuous symmetry is rotation invariance. So the idea is you take those organisms, and as I said, it doesn't have to be organisms. You could do this with little motorized go-karts. If you threw a million motorized go-karts on the floor of this room and they had interactions that made them tend to line up, that would be a system that I'm trying to describe here as well. Okay? So you take your self-propelled entities, living organisms or whatever they are, you throw them down at random in some big space, you give them only short-range interactions, and you let them run for a while. And if they go into a state where they're all on average moving in the same direction, and that direction was picked out by them, not by you telling them externally which way they should go, that's what I mean by flocking. OK? Is everybody clear on that definition? By the way, I was told that you've all been asking lots of questions, and that's really good, and you should keep doing that. OK? So any questions about what I mean by this so far? OK. So what I want to tell you about this, and VSEC actually made a point of this when I first heard him talk about this 20 years ago, is that if you're a condensed matter physicist or a statistical mechanic, and somebody tells you that this happens in 2 dimensions, you should stand up and you should be utterly baffled. You should be absolutely astonished by this. And the reason for that is that we don't know a lot of things rigorously in physics. But one of the things we do know rigorously in physics is something called the Merman-Wagner theorem. That's why they call it a theorem. And on the face of it, that theorem would seem to say that this sort of phenomenon, that is spontaneously breaking a continuous symmetry in 2 dimensions with only short-range interactions, is impossible. That's actually a theorem. So how can this be happening with these moving entities? Well, the short answer for that is that, like all theorems, you have to read the fine print. And if you read the fine print of the Merman-Wagner theorem, it says that this applies to systems in equilibrium. Now, a system of self-propelled things, living organisms, whatever, is a system that's out of equilibrium. I mean, there's a reason when somebody dies, you use the phrase cold and dead, right? Because if you're in thermal equilibrium, you're dead. Okay? So if you're not dead, and obviously you have to be not dead in order to move, you're necessarily automatically out of equilibrium. Okay? So the Merman-Wagner theorem doesn't apply, and that's why it's possible in 2 dimensions. And that's one of those answers that maybe makes you feel a little better, but doesn't explain anything. What is it about the non-equilibrium aspect of this problem that makes it possible to apparently violate this theorem? Makes it possible to get long-range order in 2 dimensions with only short-range interactions? Well, it turns out, and you won't be too surprised to hear this, that the non-equilibrium aspect is the fact that these creatures are moving. That motion leads to one of these phenomena that, in a phrase I really love, is very well known to those who know it. Most people don't know it. It's a phenomenon called breakdown of linearized hydrodynamics. It's a sort of curiosity. It had previously been known about as a curiosity of the hydrodynamics of some liquid crystal systems and also of 2-dimensional fluids. And it was, as I say, it was thought of as a curiosity, but it turns out that for a 2-dimensional flock, it's absolutely crucial. If you didn't have this bizarre phenomenon, and don't worry about it if you don't understand what this means, because I'm going to explain this in immense detail, you wouldn't have 2-dimensional flocking. Okay? It depends crucially on this phenomenon, and the breakdown of linearized hydrodynamics stabilizes the long-range order in a flock.
In a 2D fluid, would an example of that be like Cascade?
Actually not. The phenomenon of breakdown of hydrodynamics, okay, so for the benefit of those of you who didn't necessarily know what he was talking about there, the energy cascade is a phenomenon that occurs in a turbulent fluid. So if we say put a giant fan on the other side of that room and started blowing air across this room at tremendous speed, it would create these huge eddies, which would generate smaller eddies, which would generate smaller and smaller eddies. That's the so-called energy cascade, and that's turbulence. Okay? The breakdown of linearized hydrodynamics that I'm talking about happens if you go the other way in length scale. Oh yeah, no, this can all happen. It's just, but the breakdown of hydrodynamics that I'm talking about happens not as you go to shorter and shorter length scales, but as you go to longer and longer length scales. Okay, which is, yeah. Oh, the inverse cascade. Yeah, it's that. Sorry. I had your question backwards. Yeah. Good question. So a short-range interaction is any action whose range is very small compared to the size of the system under consideration. Okay. And I should say that all these theorems and so on apply in the limit where the size of the system goes to infinity, the thermodynamic limit. So any system with finite range interactions between the creatures, if you make it big enough, will be in this limit. Okay. Now, you can get a little fancier. The argument also applies if you have interactions that go out over infinite distance, but their strength falls off sufficiently rapidly with distance. If it falls off exponentially, for example, it would be a short-range interaction. It can even fall off like a power law as long as the power is sufficiently big. I'm not quite sure for flux how big that power has to be, but say power of 6 or bigger would be fine. So Leonard-Jones interactions or something like that would still be covered by this. Okay? Any other questions? Okay. So this is what I hope to make you understand in these 3 lectures. Okay, so I've already told you what flocking is. I'm going to start out by describing a microscopic model, the VSEC model. I have 2 motivations for doing this. The first one is just I want you to have some concrete idea of the kind of dynamics that I want to be describing. Okay. Now, the theory I'm going to be describing is much more general than the VSEC model. It's going to apply to any system that has what I consider the 2 most important features of the VSEC model, both of which I've already talked about. The first one is rotation invariance. That is that the creatures don't have a particular direction they want to go. All they want to do is follow their neighbors. So their dynamics doesn't distinguish between moving north, moving east, moving south, moving west, or moving anywhere in between. Okay? And the second thing is that the interactions are local, that we have short-range interactions, as we've just been discussing. The second reason I want to introduce it is that Christina is going to speak this afternoon, and she's going to do something that's much, much harder than what I'm going to try to do today, which is she's going to tell you how to derive these equations by starting with these microscopic rules. That's an amazing thing. It's amazing that it's possible to do that. It's also amazingly hard. Okay? I'm going to tell you how to just make the equations up. Okay? Now, of course, when you make things up, you have to put in some fudge factors. Christina can actually calculate those fudge factors. I can't. Okay? But you can get a lot of information without being able to calculate the fudge factors, and that's obviously what I'm going to focus on in my talk. Okay, but that's an advertisement. Come back this afternoon, and you'll see some amazing things. Sorry? This morning. It seems like afternoon already. Okay. It'll feel like afternoon by the time I'm done. Okay, so once I describe the VSEC model, I'm going to talk about the Merman-Wagner theorem, which raises the fact, which, as I said, is the theorem that makes it sound like 2-dimensional flocking should be impossible, which raises the horrifying question, are birds smarter than nerds? And then we're going to talk about our continuum theory, which we use to describe not just the VSEC model, but any model that has these 2 features. Any system of self-propelled entities that tend to align that has these 2 features. And we derive that more or less by analogy with the Navier-Stokes equation. And I'll tell you about how you use the symmetries to bury your ignorance, bury the fact that I don't know how to do the kinds of calculations that Christina can do in a few parameters. Okay? And that fundamentally is the whole game in hydrodynamics. There's a lot of complicated stuff going on very short length scales. So if you have a flock of 1 million flamingos, if you try to figure out what's going on the scale of 1 or 2 or 3 flamingos, that's incredibly complicated. But if you want to know what's happening on the scale of the entire flock, it turns out that's much, much simpler. And all the things you don't know about what's going on the scale of 1 and 2 flamingos can be buried in a few parameters which you can just fit to experiment. And most of what goes on you can describe without even knowing what the values of those parameters are. Okay, and finally, once we have the continuum model, we'll solve it, and we'll show that birds are not smarter than nerds, and that because this is a moving system, you can get around the Merman-Wagner theorem in 2 dimensions. Okay, so that's the program. Oh, I don't need to do that. Great. Okay. All right, so let's start. So this is the model that Wiesek cooked up to provide an example of how self-propelled things might flock. Okay. So it's a computer simulation. Okay. It's actually what's called a discrete time cellular automaton, which is one of those incredibly technical terms for a very simple idea. Okay. So the idea here is that each creature is a point carrying an arrow. The arrow indicates the direction the creature is going to move in. And all the creatures carry watches. The watches are like old-fashioned, do you guys see this sort of thing anymore? An old-fashioned analog clock with a second, oh, there's one back there. Terrific. Okay, look at that clock. Okay, every second, the second hand jerks forward once. Okay, every one of these creatures has one of those on its wrist or its wing or whatever it has, its fin. Okay, and they're all synchronized. So they all click at exactly the same time. So these creatures are flying along, and when their watches click, they identify their neighbors. And the way they identify their neighbors is they just draw a circle around themselves of some radius, and we'll choose our unit of length so that that radius is 1. And anybody that's inside that circle is a neighbor. And they try to follow them. And so what I mean by following them is they can observe the direction of the arrows of their neighbors. And so what they do is they just take the vector sum of all those arrows and adjust their arrow to point in the direction of that vector sum. Okay? Very simple way to follow your neighbors. Everybody does that at the same time. And then until the clock clicks again, they will just move in that direction at a speed, where do I have it? V0, which is the same for all the birds. Okay? And then the clock clicks, and you repeat the process. Okay. Now, as soon as you describe this, people in the audience start raising their hands and saying, well, what about if you made them go at different speeds? What about if you made them try to avoid bumping into each other? There's a million different bells and whistles you could put on this rule. And believe me, most of those bells and whistles have been put on these rules in various simulations that people have done. What I'm going to try to argue today is that most of that doesn't matter. So it's perfectly OK to think about a model that's as simple as this. Yeah? OK, well, they do. OK, there's an aspect of the rule I didn't tell you about. I think I'm not going to answer your question just now, but I will in a minute. OK. Wiesek added errors. Okay, so the idea is the birds try to move in the same direction as their neighbors, but they make mistakes. Okay, he incorporates the mistakes just by adding a white noise vector to the vector sum of all the velocities of all your neighbors. That error is taken to have 0 mean, which means that the birds are equally likely to make an error to the right on one time step as to the left. It has no memory, so the error you make on one time step is uncorrelated with the error you make on subsequent time steps, and which is shown down here. So there's only one parameter in that noise, which is its mean squared amplitude, which we take to be delta. So if delta is small, the creatures are doing a very good job of following their neighbors. They're making very small mistakes. If delta is big, they're not doing a very good job of following their neighbors. Okay. So that's one source of error in this. I suspect that what you're asking about is what happens if during the second between clicks, their direction of motion wanders. That's not included in the Wiesek model, but of course you could include it. And I believe it wouldn't make a difference. It would change the exact values of certain parameters in the hydrodynamic theory. It would change the scale of the fluctuations, but it wouldn't change the form of the equations, and it wouldn't change the scaling of anything, provided the noise was small enough that the system stayed ordered. I should say, by the way, that I'll get to your question, Christina. I just want to make a little plug here. Okay. A lot of times during these lectures, I'm going to say, people are going to ask me about things, and I'm going to say, that doesn't make a difference. Now, that's a bit like saying the water in this bottle is described by the Navier-Stokes equations, the equations of fluid mechanics. And the temperature in this room doesn't make a difference. Well, that's true as long as the temperature in this room stays above 32 degrees Fahrenheit or 0 degrees Celsius. If it goes below that, that obviously ceases to be true because the water ceases to be a fluid. It goes into another phase. Okay? I actually didn't plan that. The same thing applies here. When I say that all these different kinds of errors you could add in don't make a difference. When I say this noise delta in the VSEC algorithm doesn't make a difference, that statement is true as long as I don't make the noise so big that it actually disorders the system, that it actually puts it into a state that doesn't have a non-zero average speed. If that happens, then all bets are off, and things have changed. Okay. The same thing is true of the other sorts of bells and whistles I talked about. If you put in strong enough repulsive interactions between these creatures, you could actually make them lock into a sort of flying crystal. People have seen this in simulations. They arrange themselves in a regular triangular lattice, and the whole lattice just flies along. That's not described by what I'm talking about either. Okay? So I'm assuming here that the parameters are staying in a range where the long distance correlations of the flock have not been changed in any way. Okay? Qualitatively. Yeah, sorry. Yeah, I suppose that's true. Yeah. I think maybe his question was more what happens if you have noise during the time interval between the adjustments to follow your neighbors. And yeah, that's right. Yeah. But in the VSEC algorithm, the noise is only implemented on the discrete time steps. It's not implemented during the motion. But all I wanted to say is that you could do that, and it wouldn't change anything qualitatively. It would make your job a lot harder, but since I'm making up parameters, it wouldn't matter to me. Yeah.
Why do you need the noise at all?
I'll get to that. Okay. Oh, actually, let me give the short answer right now. The Merman-Wagner theorem only applies to systems with noise. If you have no noise, you won't be surprised to learn that this algorithm will eventually make everybody move in exactly the same direction, and then there's no subsequent dynamics. The whole thing just moves along at a uniform speed. The question I want to address is, if you make mistakes, is the order robust against those mistakes? Okay. You don't remember this, but in the early half of the 20th century, which I don't remember either, people wondered whether it was actually possible in an equilibrium system, even in 3 dimensions, to have long-range order at finite temperatures. And it was a really big question that wasn't settled until I think the Onsager actually solved the 2-dimensional Ising model. Okay? So that's one of the big questions in statistical physics, is long-range order robust against noise? And that's the question that makes 2D, that's the question that makes 2D flocking so interesting. If you don't have noise, it's kind of trivial. Even a 1-dimensional flock could order. Okay? But in the presence of noise, it becomes harder, and that's what makes it more interesting. And it's also interesting to study fluctuations. And I think any real creature or any real molecular motor or whatever self-propelled entity you think of, there's always going to be some noise. Okay. So you have to include it to be realistic, and it also is really, really interesting. So that's why I include it. Yeah?
Is there anything to stop the flock splaying out to its size? The edge particles? Does averaging
Yeah.
stop that happening?
Yeah. In these simulations, there's something very effective at stopping them from spreading out, which is you put them in a box. Okay. In fact, usually in these simulations, people put them in a very artificial kind of box with periodic boundary conditions. The box will be, say, this blackboard, and a bird that flies out on this side reappears on that side. One that flies out the top reappears at the bottom. Later on, I'm going to show you the results of a few simulations not done by me, in which we used mixed boundary conditions, where if the creatures hit the sidewall, they bounced off. But when they disappeared at the top, they reappeared at the bottom. That has the nice feature that if the flock can achieve long-range order, you know it's going to either be moving straight up or straight down. And that's a very helpful thing for analyzing the result. It doesn't get you around the Merman-Wagner theorem, because even though you have these side walls to align you, you've got to have long-range order for the information about that wall to penetrate to the center of the flock. Okay. So good question. But anyway, so of course in real flocks, you don't have periodic boundary conditions, you don't have walls. What holds them together? That's an interesting question that's a current topic of research. And come back in 10 years and maybe we'll have an answer for that. The assumption is that there's something like a surface tension that holds them together, just like there's a surface tension that holds liquid drops together. But it's a non-equilibrium system, so we don't really know how to do that yet. But we're working on it. OK. So this is the VSEC algorithm. Any questions about this? And as I said, if you want to imagine variants on this, there's a million different bells and whistles that I'm sure you can all think of. OK. So the thing I want you to note about this algorithm is it's short-ranged, right? By construction, you only see your neighbors within a distance one of you. We're going to eventually consider flocks whose length on the scale of that interaction range is enormous, is much, much bigger than 1, which means we're going to consider flocks with a large number of creatures. Uh-oh. What did I just... okay. Okay, so it's local, as I said, and it's also a rotation invariant dynamics. Okay, there's nothing anywhere in this dynamics that tells you there's a particular direction the creatures want to move in. Okay, and in fact, you would suspect, and it's easy to confirm this in simulations, that if you started with identical initial conditions and ran, if you run this simulation a million times, any given final orientation for the motion of the flock is equally likely. Okay, so that's the algorithm. Any questions? Yes. Oh, I'm sorry. So this vector eta I is a vector. So alpha indicates the Cartesian component. So in 2 dimensions would be x and y, in 3 dimensions be x, y, z, so on. The index I labels the birds, the entities. Okay. Any other questions? All right. So that's the algorithm. So what happens when you do this? Well, what happens is something which, as I said, if you're not a trained statistical mechanic, doesn't seem very surprising. You start an algorithm like this off at t equals 0 with the creatures just plunked down at random on a 2-dimensional plane and with their arrows all pointing in random directions. Now, if you take that system and you ask, what's the average velocity of that flock? Average defined as just sum up all the velocity vectors divided by the number of birds. Well, that average is obviously, if there's a lot of birds, going to be very, very close to 0. In fact, it's going to be of order 1 over the square root of the number of birds. And now you run this VSEC algorithm, and what happens? Well, after a while, what happens is all the velocity vectors line up. They all wind up moving in the same direction. And as a result, the average velocity is non-zero, and the direction they pick to move is completely arbitrary. You run this simulation a million times, you'll get a million different directions, and there's no particular preference for any one direction over another. And that's not surprising, because you didn't put in such a preference. Okay? The system is spontaneously breaking the rotation invariance of both the initial conditions and the intrinsic dynamics. Okay. Yes? I'm sorry? If you use different noise, yeah. Obviously, if you use the same initial condition and the same noise, then you'll always get the same velocity. But slight changes in the initial condition, slight changes in the noise, probably even numerical error noise is enough to make you pick a completely different direction. OK, so at first glance, that seems unsurprising. You created an algorithm to make the creatures move in the same direction, and they all moved in the same direction. What's the big deal? Well, the big deal is that in 2 dimensions, in the presence of noise, this is supposed to be impossible. It violates the Merman-Wagner theorem. So what do we mean by the Merman-Wagner theorem? OK, which, as I said, raises the horrible question, are birds smarter than nerds? OK, so this is one of the few experiments I've ever personally been involved in. It's an experiment that's done every year at the American Physical Society March meeting. So what happens is 20,000 physicists descend on some poor, unsuspecting city and go to sessions all day. And then at the end of the day, they all gather in the giant lobby of some giant hotel in a city that none of them have ever been to before. Okay? And they want to go to dinner. And because the chain of interpersonal connections percolates, that is, I know Leo, Leo knows 20,000 other people, those 20,000 other people know 20,000 other people, everybody is going to wind up going to the same restaurant. Okay? And of course, no one knows where the restaurants are because we've never been to the city before. So what you essentially wind up doing is you start walking off in a random direction trying to find a restaurant. But actually, that's not what happens, because being physicists, being intelligent people, you don't want to start walking before you know where you're going. At least you want to have a direction that you're all going to move in. So what happens is everybody stands on the floor and points in some direction that they want to go looking for a restaurant in. And of course, that direction is chosen completely at random. But then, of course, you want to arrive at a consensus. You want to all wind up picking a direction so you can all finally start walking off and get dinner. And so you start pointing in the same direction as your neighbor. And you could imagine using an algorithm almost exactly like the VSEC algorithm that I just described to try to arrive at that consensus. You draw a circle around yourself, or you just look at everybody you can see on the lobby of this hotel and try to point in the same direction as they do. Now, even though we're all intelligent people, we all have PhDs and so on, we presumably make mistakes. Right? We don't perfectly follow the direction of our neighbors. So you could set up an algorithm almost exactly like the VSEC algorithm with the same parameter delta describing the noise strength, and let this run and see what happens. Well, I'll tell you what happens. If you've ever been to the March meeting, you already know. You never get dinner. And the reason you never get dinner is that everybody does not, it never happens that you all wind up pointing in the same direction. And in fact, if you look at the direction that any one individual is pointing, and you ask what's the typical mean squared fluctuations in the angle that that person is pointing in, you'll find out that that's roughly this noise strength delta times some constants like 2 pi or things like that, times the logarithm of the linear extent of this hotel lobby, or the logarithm of the square root of the number of physicists at the meeting, if you want to think about it that way. Okay? And the point is that that number is large. So even if your noise is very, very small, even if delta is tiny, this product is bigger than pi, or bigger than pi squared. And so the direction you're pointing wanders all over the place. The direction everybody else is pointing wanders all over the place. And there's no long-range order, and you never get to move, and you never get dinner. Okay? And that's the Merman-Wagner theorem. The Merman-Wagner theorem says this must happen. Okay? And you see, you can't beat it. You might think, well, we can just make smaller errors. Well, if you make smaller errors, but you make the system bigger, eventually this product is always going to get to be bigger than pi squared, and you're always going to be disordered. Okay? Yes, yes, a small system can do this. That's right. And that's what I do now. This is about the biggest kind of meeting I'd ever go to. We have a chance of getting dinner tonight, I think. Yes, yeah. Theta is the angle measured with respect to some arbitrary reference direction. Yeah. Well, you can actually define angles in a way that they wind around, right? You can, if I start, say I start out pointing that way and I say theta is 0, right? And I make a series of errors and I wind up at 10 degrees. Then I make another series of errors and I wind up at 20, okay? Eventually, when I get all the way around, I'll wind up at 360. And if I insist that I'm going to keep always evolving the angle by going to the integral multiple of 2 pi that's closest to where I am, then it'll just keep growing and growing. That's what I mean by the angle going to infinity. Okay, it gets a little. You have to think about the history of how you define it. It doesn't really matter. The important point is that no matter how small your noise is, if you make the system big enough, it's going to get to be bigger than pi. And once that happens, the system's disordered. Is there a question? I'm glad you asked that. Audience plant. Okay. The difference between this model and the previous one is that here you point, but you don't move. That's the only difference. This is exactly the VSEC algorithm, except you never move. Another way to think about it is this is the VSEC algorithm in the limit where the speed that the creatures move at between clicks of the watch goes to 0. Okay. So this tells you the fact that this cannot order, but the flock can. Or let's put this another way. Suppose we decided not to try to be wise-ass physicists and agree on a direction of motion before we went, but we just gave people the instruction, just start walking and try to follow your neighbors. Then you'd get to eat. Okay? This collection, take the same individuals with the same noise strength and the same range of interactions and introduce the sole modification that instead of trying to point in the same direction, you try to move in the same direction, then you can do it. That works. Okay? So that's the result, and the question is why? Moving and pointing sound like almost exactly the same thing. What's the difference? That's what we want to understand. Well, maybe they're dumber. Sometimes you're better off being stupid, right? You can overthink things, and that's what the physicists are doing, I think. They're overthinking things. If you just started walking, you'd be fine. But you try to be smart and plan, and that backfires. OK, so before I explain why motion makes this possible, let's understand why it's not possible if you just stand there and point. OK. And now, there's a classical equilibrium statistical mechanics derivation of this that involves Boltzmann weights and Hamiltonians and energies. And that's the simple way to understand the equilibrium problem. Unfortunately, it's so rooted in the equilibrium system that it gives you no clue as to how to treat a non-equilibrium system. So what I'm going to do instead is something that's very perverse. I've never seen this derivation of the Merman-Wagner theorem in any textbook, probably with good reason. It's a very bizarre way to derive it. But if you can understand this, then you can understand not only the Merman-Wagner theorem, but why motion enables you to get around it. So let's try. So this is a purely dynamical explanation of the Merman-Wagner theorem. Okay. Basically, what happens is that if you're in two spatial dimensions or less, it turns out the Merman-Wagner theorem also applies in one dimension, errors accumulate faster than they're dissipated. Okay. And let me try to explain what we mean by that. Here's just a rewrite of the evolution rule for the direction the pointers are pointing, the angle that they make with some reference direction. Okay. So the original rule was the angle you're going to make at time t plus 1 is the average of the angles of all your neighbors at time t, plus a noise. Okay. So all I did was I took that equation and I subtracted the angle you were making at the previous time step from both sides. Okay. Now, if you think back to your first calculus class, you'll realize that this difference begs to be approximated as the time derivative of theta. If you think back to your first E&M class, you'll recognize this combination, the average of some field over a local region minus its value at the center, as the discrete approximation to the Laplacian. So once you make those two realizations, you'll realize that this dynamical equation can be rewritten as a noisy diffusion equation. Time derivative of the angle is Laplacian of the angle times some diffusion constant plus a noise. And if you can't see that, just one simple way to derive that is imagine that the creature you're considering and its four nearest neighbors were arranged on the sides of a square lattice, and just expand out those differences, and you'll realize that you can rewrite it like that in first order of approximation and derivatives. Okay? Any questions about this? Yeah. Okay. Maybe I should go through this then. Okay, so here's an example where the central creature and its four nearest neighbors are arranged on these sides of a square lattice. Okay, so here's the central creature, here's the four nearest neighbors. So let's look at the right-hand side here. Okay, so the average of its four nearest neighbors is just 1/4 of the sum of those four angles. Okay, and now we're subtracting the angle of the creature at the center. So now I'm just going to group. I'm going to take this subtracted term and group 1/4 of it with each one of these four terms. Okay? So theta 1 minus theta I, well, here's theta 1, here's theta I. That difference is roughly the x derivative of theta. Okay? Likewise for the other four terms. Okay? So when you group those things, this becomes the x derivative of theta evaluated here minus the x derivative of theta evaluated there. That's the x derivative of the x derivative of theta, which is the second derivative. Same thing for the y components in the vertical direction, and so you just get the Laplacian. That makes it look like it depends on having these things positioned at these four magical sites, and one of the things they teach you in E&M is that it doesn't depend on that. You can have any arrangement to these points, and this will be a good approximation to the Laplacian, provided only that this field is varying slowly in space.
But this depends on, in the average, you don't include your step. In average, you include your step, then it's not. It cancels.
But the algorithm does. Let me mull that one over and get back to you on that, okay? All right. Anyway, that's the idea. Okay, so basically the dynamics of this angle is a noisy diffusion equation. Okay, so what do we know about diffusion equations? Well, there's two important things you know about diffusion equations. The first one is that they're slow, right? You know that if you have a cup of black coffee and you want to add milk to it, you don't just pour a drop of milk into the coffee and then wait for the milk to diffuse over the cup of coffee, because you would literally have to wait about a day and your coffee would be cold and disgusting by then. Okay? So you can actually quantify how slow a diffusion equation is just by power counting. Okay? Just looking at this equation, roughly speaking, theta over time goes like theta over distance squared. So that says distance squared goes like time, or distance goes like the square root of time. And in fact, if you track the milk in your cup of coffee, you would find that if it started out with its concentration peaked in some very small region, after a time t, it would spread out over a region whose size grows like the square root of time, which is, of course, slow and gets slower and slower as the square root of time, as time gets bigger and bigger. Okay? So that's the first thing to know. So the same thing is true of these angles. They diffuse very slowly through the collection of pointers. The second thing about the diffusion equation is it conserves the integral of whatever it is that's diffusing. Okay? You can just take the volume integral of both sides, and you'll see that the right-hand side, if you ignore the noise, is just a surface term. And so if your surface is infinitely far away, you have periodic boundary conditions, or surface to volume is negligible, you can neglect that, and the total integral of the field, in this case the angle, over all space, doesn't change over time. Okay? So stuff is conserved. All right, so what does that mean? What does that have to do with the Merman-Wagner theorem? Well, to get an understanding of that, let's first consider what would happen if you turned off all the noise in the VSEC algorithm. If you tried to do something that really favored order. Okay? So turn off all the noise in the VSEC algorithm. Start with an initial condition where everybody's pointing in the same direction, except one person. Okay? That person at the center is pointing off by some angle theta naught. Okay? And now ask what happens if you let the algorithm run for a time t. Well, since the angle obeys the diffusion equation, what's going to happen is this initial error of theta naught is going to diffuse out a distance that grows like the square root of time. So that means that everybody within a distance of order the square root of time is now also going to be making a mistake. Yes?
In this, are you keeping that direction?
No, no. So I'm starting with this initial condition, and then everybody, including the initial creature, good question, is evolving according to the VSEC algorithm. Okay? So on the first time step, this guy is going to immediately point in the direction that everybody else is pointing, but unfortunately by then he's going to have contaminated all his neighbors who are now going to be pointing off by some amount. And then that's going to spread out. Okay. So at a much later time, the error is going to have infected everybody within a distance of order proportional to the square root of time of the original error maker. Okay. Now, of course, the error is going to have gotten smaller because the volume integral of the angle, or equivalently the sum of the angle over all the birds, is conserved. Okay. So effectively what's happened is this original error of theta naught is now going to be spread over all the birds within this circle. That makes sense? It's going to be evenly divided among them all. So the angular error that any one of them is going to be making is going to be roughly the original error of theta naught divided by the number of birds in that circle. Okay? Now, how many birds are there in that circle? Well, that's easy. If the density is roughly uniform, the number of birds in the circle is going to grow like the radius of the circle to the power d, where d is the dimension of the system under consideration. So if this is a two-dimensional system, it's going to grow like the radius squared. If it's a three-dimensional system, it'll grow like the radius cubed. And if you're a theorist, you'll think about four-dimensional systems, it'll grow like radius to the fourth, and so on. Okay, I'm going to take a break in a couple of minutes. But before I do that, I want to make a point here. So if the error is falling off like 1 over radius to the d power, and the radius is growing like the square root of time, then the error is falling off like 1 over time to the power d over 2. And I want to call your attention to two things about that result. The first one is that it depends on the dimension of space. And that's why the Merman-Wagner theorem depends on the dimension of space. As you go to lower and lower dimensions, this fall-off gets slower and slower. And that's why it's harder to order a low-dimensional system than to order a high-dimensional system. Okay, that's the first point. Second point is that it's slow, right? It's not falling off exponentially. There's not some characteristic time after which all the errors will go away. It's falling off like a power law, and that power law is getting very small as you go down in dimension. In fact, by the time you get to dimension 2, it's just falling off like 1 over time, which is very slow indeed. Okay. So after the break, I'm going to talk about what happens if you now really do the VSEC algorithm, where while the errors are trying to decay by this very, very slow process, more errors are constantly being created. And what you'll find is that if you're in high enough dimension, this decay of errors can compete with the accumulation of noise and actually suppress the accumulation of errors, and you can get long-range order. But if you're in low enough dimension, you can't, and the critical dimension where you cross over between those two is 2. Okay, and that's the Merman-Wagner theorem. And we'll do that after a 5-minute break. Thanks. Mm-hmm. Well, the angle obeys the diffusion equation. And in a diffusion equation, the thing that's diffusing is conserved. Right? Just that, let me go back. Okay. That's just this. Okay, so the angle obeys the diffusion equation. So let's imagine we turn off the noise.
Okay.
Okay, so now I just take the volume integral of both sides. Okay, so the volume integral of this side is just the time derivative of the volume integral of the angle. You with me? Volume integral of this side is the volume integral of the Laplacian. But the Laplacian is the divergence of the gradient. So you apply the divergence theorem, and that says that this is the integral of the gradient of the angle dotted into the surface over the surface. Okay, so now so keep that in mind. Now let's go back to the picture. Okay, the surface here is way out here somewhere. Okay, so there's no this initial error hasn't gotten out there yet. So out there, all the angles are still uniform. Okay, so the gradient is 0. So there's no this term is 0.
Okay.
Okay, and it will be 0 until that region grows out to the boundary of the system.
But I mean, that's in a specific scenario.
No,
Where
it's
these are
what's specific about it? All it depends on is that the system is big.
But you're starting out in the ordered state then.
Yeah.
Okay.
Yeah. I'm trying to first understand. Well, what we're trying to ask is if you start. Another way to ask the question is if I start with the ordered state, will I stay there?
Okay.
Okay.
Right.
And as a first step towards understanding that, I'm asking if we just make one error at time 0 and then we turn off the noise, what happens to it? Okay. And you see, so that's the case I'm trying to discuss.
I guess
okay?
I missed the caveat with starting in the ordered state and not having noise.
Well,
that's why it didn't
okay.
make sense to me.
This is true. This is true regardless of what state you start in. Okay. And it says that this volume integral will be conserved except for what current you have through the surface.
But also without noise. That's true.
Yeah, that's right. Yeah. Noise will then generate a change in this, and the question is, will that change accumulate and make you make very big angular errors, or will it be suppressed by the diffusion and keep the error, which will keep the error small? And that's the balance I'm going to do after the break. All right. Okay.
Yeah, I think about even you include yourself in the average, it's due to Laplace.
It should be,
Yeah,
but I was getting a bit.
Because in the average,
Yeah, of course, that's it. Yeah. You'll change the diffusion constant a little bit, but that's all. Yeah. Well, no, whether you include yourself or not, you're not. The original error maker is not fixed.
It's not fixed. No.
Right.
The original error maker, in that diagram you had over here, everyone's straight, that's slightly off. The next update, this guy is closer to everyone else, but everyone else is also slightly.
Right. Now, right. If you don't include yourself in the averaging, then on the next step, the original error maker will be perfectly straight. But it won't last, because on the next time step, he's going to see his neighbors making errors. And
Is it then sufficient to understand why this fixed itself when this
thought was one result would be at 2 p.m. There was a typo in the schedule. I know you sent out the email. It's at 2 p.m. like every other day.
Okay. I want to start off because there seems to have been some confusion. Right now, everything I'm saying is about pointers. Okay, I haven't yet moved on to talking about movers. Okay, so the point I left you with was that because this angle field is described by a diffusion equation, errors that you make decay very slowly. And so now I just want to see, yeah. So now let's ask what happens if we turn the noise back on in the VSEC algorithm. And let's consider a flock of radius r. Okay. Well, what I showed you is the diffusion equation will, any errors you make inside this flock will be conserved until enough time has passed for those errors to diffuse all the way to the boundary, right? Because that's the property of the diffusion equation. You can only change the volume integral of the angle by things escaping through the surface, okay? Or by noise, by generating them by noise, okay? So any noise-generated errors that occur inside a flock of, inside a region of radius r, or a collection of pointers of radius r, can only start to decay on the time scale, on the time it takes for those errors to diffuse all the way across the system, which goes like the size of the system squared, because it's a diffusion equation. Okay. So let's ask, in that time, how many errors are made inside this flock? I shouldn't call it a flock because they're not moving, inside this collection of pointers. Okay. Well, each individual pointer makes an error on every single time step. So the number of errors made by each individual pointer, I'm calling the pointer spins here, that's betraying my statistical mechanics background. The number of errors per spin, the number of errors per pointer goes like this time, so it goes like the radius squared. So the total number of errors that are made is that number per pointer times the number of pointers. The number of pointers, of course, goes like the radius to the power d. Okay. So once again, the dimension of space is entering this argument. Okay. So the total number of errors is the number of pointers times the number of errors per pointer, and that goes like the radius of the system to the d plus 2 power. Okay? What's the sum of all those errors? Well, of course, some of them are errors to the right, some of them are errors to the left, so they're going to tend to cancel. But when you add random numbers, you typically have some residual left over, and the typical size of that is the root mean squared error, which is just scales like the square root of the total number of errors. Right? Basic result from statistics. So the RMS error goes like the square root of r to the d plus 2. So the error per pointer goes like that number divided by the number of pointers, which goes like r to the d. Okay? You'll notice this is a very simple argument. You're just basically counting on your fingers. And if you look at that ratio is going to give you the typical angular error that an individual pointer is making. Okay, is that clear? Well, what is that angular error? Well, you just take this ratio, and it's simple arithmetic. It goes like the radius of this collection of creatures to the 1 minus d over 2 power. Again, the answer depends on dimension. And now you'll see something very obvious happens. If d is bigger than 2, as the size of the system goes to infinity, as r goes to infinity, this mean angular error goes to 0. That means the system's going to be able to order. So if the March meeting was held in a hotel with transparent floors and ceilings, and we spread out over all the floors so we became a 3-dimensional system, we'd be able to get dinner. Okay? But in 2 dimensions, well, if you're in a 1-dimensional system, of course, this would go like r to the 1 minus 1/2, goes like the square root of r, would go to infinity as r went to infinity. In fact, that'll be true in any dimension d less than 2. So you cannot have long-range order in d less than 2. D equals 2 is the marginal case. You might think that in that case, the angular error goes to a constant as the size of the system goes to infinity. But if you think back to when you did calculus, a power of 0 typically doesn't mean a constant. It typically means a logarithm. And that's the logarithm that I showed you several transparencies ago when I was talking about what happens at the March meeting. Okay? And that's what happens here. The mean angular error in 2 dimensions goes like the logarithm of the radius. This should be an r, not an l. And that goes to infinity as the radius goes to infinity. So again, you don't get long-range order. So that's the Merman-Wagner theorem. So in a nutshell, why can't you order in 2 or lower dimensions? It's because the errors accumulate faster than they can be dissipated. And that's because they can only be dissipated by this slow diffusive process. Okay? So that's the story. In equilibrium, when you don't move.
So when you move, you dissipate the errors faster than that?
Exactly. That's the whole point. Okay? And the question is how? You know, what does the motion do to make you do this? But that's basically the bottom line, is that you can dissipate the errors faster by motion. Okay, so we didn't have that insight originally, Juhai and I, when we started thinking about this. So we started trying to formulate this in a way we were familiar with. Okay? And what we were familiar with was fluid mechanics. Actually, there were two things we were familiar with. We were familiar with fluid mechanics, and we were familiar with dynamical models for magnetic systems, which is another way to say pointers. Okay? So let's talk about fluid mechanics first. Okay? Well, let's talk about flux first. Okay? One way you might imagine doing this is being a genius and trying to exactly solve the problem of what are the dynamics of a million birds obeying the VSEC algorithm. That's pretty hard. Even Christina, to do this, has to make some uncontrolled approximations. Okay? And furthermore, it's a lot of work. Okay? And I'm not that inclined to work that hard. A second drawback of this approach is that if you start adding bells and whistles, and remember I said you can add a million different bells and whistles to this algorithm, every one of those is going to change that microscopic calculation. Okay? A third problem is that in a lot of experimental systems, you don't even know what the microscopic rules are. You know, I don't know the psychology of a bacterium. So I don't necessarily know how to describe, you know, what the interactions that determine their motion is. Okay? So in fact, when you start thinking about flux, if you're a physicist coming into what's basically a biological discipline, you're in a position very similar to the position that physicists and mathematicians were in the early 19th century when they were trying to understand fluids. Okay? In fact, they were really up against it. At that time, there was no theory of atoms and molecules. In fact, I'm not sure they even knew that fluids were made out of atoms and molecules. If they did know, they didn't know how big the atoms were. They didn't know what the interactions between them were. Even if they'd known that, they couldn't really have done much with it because they didn't have statistical physics then, right? I mean, Boltzmann hadn't been born in the 1820s, much less committed suicide. So, you know, they were up against it. They didn't have the benefits of modern technology to help them solve it. They couldn't just simulate things. Probably a good thing, actually, at the time. So you would have thought this problem was hopeless. But in fact, what these two guys, Navier and Stokes, did was formulate a pair of very simple equations. You can write them down in 2 lines that are so powerful and so complete that any time today anyone wants to understand the fluid mechanics problem, be it the behavior of the atmosphere of the sun or the atmosphere of the earth or the oceans or oil flowing through a pipe or any plumbing, any fluid mechanics problem you want, they do not simulate the motion of individual atoms. They numerically or analytically solve the equations that these guys wrote down, okay, without knowing anything about the underlying microscopic dynamics of fluids. So Juhai and I looked at that example and we thought, that's great, that's what we want to do. We don't know anything about birds, so let's try to formulate a theory of birds that's going to be as complete as the Navier-Stokes equation was for fluids. And our ignorance may actually help us. Okay, so that was the idea. So crack out the history books. How did these guys do this? Well, the first thing they did was to formulate it as a continuum model. Now, I don't know whether they formulated fluid mechanics as a continuum model because they thought fluids actually were a continuum, you know, that the air in this room, for example, filled all the space, or whether they were just making an approximation based on the fact that there were a lot of air molecules in this room. It doesn't really matter. The point is that anytime you have a system consisting of a huge number of individual entities, on sufficiently large scales, you can approximate it as a continuous medium characterized by 2 fields. One of them is the local density. How many creatures per unit volume are there at this point in space in this time? That's rho of R and T. And a local velocity, which also depends on where you are and the time. You know, how fast is the air here moving? What's the wind speed here? What's the wind speed over here? Okay? Those are the fields that they use. Now, of course, this description is worthless if you want to understand the motion of an individual molecule, or if you want to look at the behavior of a few molecules, or if you want to look at anything on a scale that's comparable to the spacing between individual molecules. Okay? But as long as you restrict yourself to looking at scales much bigger than that, in our case it would be much bigger than the interbird distance, and time scales much bigger than all the microscopic time scales. So for example, in the VSEC algorithm, the time between successive clicks of the clock, then this continuum approach ought to work. Yes? There could be if you get near the phase transition here. Okay, so I haven't said this, and I'm not going to talk about this in these lectures, but one of the things you can do in the VSEC algorithm, or any algorithm where you have noise, is at least in a computer simulation, you can crank the noise up. And if you crank it up enough, you'll disorder the flock. And if you go near that transition, there will be a long length scale that will get bigger and bigger and will eventually diverge, and that will be the length scale that appears over here. Okay. So what I'm imagining here is imagining a system that's well below that transition, and then this would be the interbird distance. But in general, it's some microscopic distance that could depend on parameters in the system. And you don't a priori know what it is. What you do know is that there ought to be some length scale beyond which this ought to apply. But sometimes it can be hard to figure out what that length scale is. That's right. OK, so a lot of people think this is a bug. A lot of people think this is a problem with these continuum approaches, because you're restricted to looking at long length scales and long time scales. And in fact, it can be a problem. If we were doing this 50 years ago, you probably wouldn't be able to simulate a flock of more than 10 or 20 birds, and you wouldn't be able to test any of this in simulations. And there are people who study flocks of, real flocks of birds, make videos of flocks of birds and study them. And it's hard to find a flock of birds that's more than 10 or so interbird distances across. So sometimes it can be hard to find a system where the length scales and time scales are long enough that you can apply these continuum approaches. So that's kind of a drawback. But the way we like to think about it is it's a feature. And the reason it's a feature, the reason it helps us is that since we know we're going to be restricted to looking at long length and time scales, it means that when we formulate the equations of motion for these two fields, we only have to keep the terms that are important at long length and time scales. In fact, it would be nutty to keep anything else, because then we'd be trying to push the equations to shorter length scales and time scales than those on which they're valid. Okay? So that means when we try to write down an equation of motion for these guys, and incidentally, there's at least two ways that I know of to write down these equations of motion. There's the hard way, which Christina does, which is to actually try to derive them from the underlying dynamics. Then there's the way I do it, the easy way, which is you make them up. The drawback with making them up is you can make up a lot of things. Your imagination is pretty rich. You need to be able to restrict somehow the number of terms you can write down. And this idea, the fact that you're looking at long length and time scales, is the most effective way we do that. We do what's called a gradient expansion. That is, we only keep terms in the equation of motion that are very low order in space and time derivatives. Because anything else is only going to be important at short length and time scales, where the whole description is nutty anyway. Okay? So that's the first simplification we're going to make. The second simplification we're going to make is we're going to assume that the fluctuations in these fields are small. Right? Apparently, in these VSEC simulations, you do get a well-ordered state, so the fluctuations must be small enough that at least the order can be preserved. So we're going to expand in powers of the fluctuations of these two fields about their mean values. The really powerful thing is that the equations we write down have to be consistent with the symmetries of the underlying dynamics. So in the case I'm talking about here, the underlying dynamics are rotation invariant, so I have to write down rotation invariant equations. And what rotation invariance means is that if I take my equations of motion and I apply a rotation matrix to all the vectors in the problem, which are the velocity vector, the position vector, and the gradient operator, which you can think of as a kind of vector, the equation should remain unchanged. So those are the rules that I'm going to apply to my rampant imagination in trying to make up equations of motion for these two fields. And if you do that, you get these equations. Okay? They're a little bit more complicated than the Navier-Stokes equations. If you've seen the Navier-Stokes equations, you'll recognize them as similar to the Navier-Stokes equations, but different in some ways. And but this is all you can get. Okay, now I want to say some things about these two equations. The second one I think you've seen before. Okay? If you wanted to say that equation in words, you would say birds are not being born or dying on the wing. Okay? Or another way to say it is the number of birds is conserved. So the local density can only change if the birds leave the region you're considering, and they do that by a divergence of the bird current, which is just the density times the velocity. That's also known as the continuity equation. Okay? That's very familiar. It's the same equation you have in fluid mechanics, and I don't have much more to say about that. Oh, except one thing, which is that in some situations, creatures are being born or dying on the wing. There are bacteria colonies where the time scale of the motion of the bacteria colony is comparable to the time scale for bacterial reproduction and death. And there, you actually wouldn't have this equation. You would have a birth and death term on this side. And that's an interesting problem in its own right. But it's not the one I want to talk about here. OK, so the hard equation is the velocity equation. So what can I say about the velocity equation? Well, the first thing I can say is a confession. We didn't actually make this equation up from whole cloth. We actually first constructed this equation by what I like to call the King Kong meets Godzilla approach. That is, I heard VSEC's talk. Yuhai and I went back to my office, and we started saying, well, what do we know about that's something like this? Okay. So the first thing we knew about King Kong was the Navier-Stokes equation. You can get the Navier-Stokes equations from these equations by crossing out a bunch of the terms. If you cross out these two terms, and that's basically it, then you get the Navier-Stokes equations. Well, I guess you have to do this one as well. Okay. So if you cross out 1, 2, 3, 4, 5 terms, you get the Navier-Stokes equations. Okay. So we wrote that down. And then we said, well, what else do we know? Well, Wiesek pointed out that this problem was kind of like the pointer problem, which is kind of like a magnetic problem. And people had written down dynamical equations for the magnetic problem. And in fact, if you take this equation and you erase these 3 terms and this term, then you get what are called the time-dependent Ginzburg-Landau equations, which are the simplest dynamical model for what happens, the dynamics of a magnet. And you can think of a magnet as just a collection of pointers. Okay? So we had those 2 equations, and then we just did what I think you young kids call a mashup. We just sort of fused the 2 equations together, and we got something that was almost like this. I think we missed these 2 terms, but then we thought about it some more and we added those in. And that was basically all we could think of, and that was it. Anything else you can think of will violate one of the rules I described in the last transparency. It'll either have more derivatives than these terms, or it will be less important in a system that's well ordered. So this is what you get. Now, we didn't write this down with any intuition at all. We just constructed it the way I described it, just making up terms. You'll notice everything in here is rotation invariant. And what that means is that, OK, so in this equation, rotation invariance means this is the time derivative of a scalar, so it's a scalar. So it has to be related to another scalar. And sure enough, if you take the divergence of a vector, you get a scalar. Okay, so that equation is rotation invariant. This is the time derivative of a vector. So every other term in this equation has to be a vector. Well, that's obviously a vector. It's the same vector. That's a vector. These things are combinations of vectors with the indices contracted, that is, dot products made in such a way that what you're left with is a vector. And if you just construct all the vectors you can make out of velocities, gradient operators, and densities, this is what you get. Okay, so it's pretty simple. Once you do that, though, you can start looking at these terms and say, well, they have some physical significance. Okay, so let's look at these. This first term here is what I call convection. Okay, it just reflects the fact that if you're a bird flying along with the flock, even imagine a flock was flying by you and you're standing here looking at it, and every bird that's right in front of you, and the identity of that bird is constantly changing as the flock goes by, but every bird that's right in front of you is going at exactly the same speed. Okay? You would say then that the time derivative of the velocity, which is actually the partial derivative of velocity with respect to time, at that point is 0. Okay? But now suppose the flock for some reason is speeding up as it goes from here to there. And you're a bird going along with the flock. Well, you, of course, will accelerate. Okay? And that physics is reflected in this convection term. Okay? Velocity dotted into the gradient tells you how fast your velocity is changing because you're accelerating along. Okay. Now, the one peculiar feature about this that makes it different from the Navier-Stokes equation is that in the Navier-Stokes equation, this coefficient is 1. Here it doesn't have to be 1 because, and this is something I should have said at the outset, I'm only considering flocks that are not Galilean invariant, which is a fancy way of saying they're moving over a substrate or through a medium that's fixed. And that medium provides a special Galilean frame of reference that's different from all others. That's the stuff that they're pushing against with their flippers or their fins or their wings to make themselves move. That's the stuff they experience friction with. Okay? And that's a special reference frame. Because that system is not Galilean invariant, an individual bird can tell the difference between an acceleration that's because the velocity is changing as a function of time and an acceleration that arises because the velocity is changing as a function of position. And that means that this coefficient lambda 1 does not have to be 1. It doesn't have to be 0 either, so that term is there. These other 2 terms are not present in the Navier-Stokes equation because they violate Galilean invariance, and they have a simple physical interpretation too. This one, div.v tells you whether creatures are converging or diverging. So imagine you're driving along a 20-lane highway, and you see cars converging in front of you. Okay? There's 2 possible reactions to that depending on your psychology. You can either think, great, this is going to be really fun. I'm going to go in there and challenge these guys, and you'll accelerate to meet those guys. In that case, this coefficient lambda 2 will be negative. Okay? Or you might be like me and say, I'm going to avoid that, and you'll hit the brake. You'll decelerate. In that case, this coefficient would be positive. Okay? So I call that the crunch anxiety term. Okay. Second thing you can imagine on the highway is you're driving along and you notice the people ahead of you are driving at 200 miles an hour. and you're doing 55. Two possible reactions to that. Great, it's going to be fun to go at that speed. I'm going to accelerate and tailgate those trucks. In that case, lambda 3 will be negative, and you'll accelerate in the direction of the gradient of the speed. Okay? Opposite reaction, you have the opposite sign of lambda 3. Okay? So those things make sense. It makes sense that creatures would have terms like that in their equations of motion. Okay, these terms. These terms turn out to be the crucial ones. Okay? Now, this first term is something you saw when you took freshman physics. When they start treating friction, the simplest model for the motion of a block sliding on a frictional surface is the time derivative of its velocity is some minus some drag coefficient times the velocity, right? And you know what that'll do. That'll make the velocity eventually decay to 0. You'll notice, however, I did not put a minus sign in front of this term alpha. And the reason for that is that my creatures are alive. So their speed doesn't have to go to 0. They have little internal motors. They have legs, wings, feet, flippers, whatever propels them. Cilia, if they're bacteria, they have some internal energy source that can actually enable them to have a kind of negative friction. So if they're going too slowly, they'll actually accelerate in the direction they're moving. Okay? And so that would mean this coefficient alpha is positive. Yes? Not quite. That's what the beta term does. Okay. So, but you did catch an important point. If that was all you had, these creatures would accelerate exponentially, and they'd eventually be going faster than light, and Einstein would be upset, and they'd be very tired. Okay? They can't do that, right? There's a limit to how fast they can move, and so what you do is you just put in a saturation term. Okay? And that's what this high order term is. And by the way, there's nothing sacred about the exact form of these terms. The important thing about them is they're in the direction of the velocity, and if your velocity is too low, you accelerate. If your velocity is too high, you decelerate, and you eventually, in the absence of noise, will reach a steady state where these terms balance. And the value of the speed at that steady state, you could choose, if you were, say, trying to model the VSEC algorithm, to be V naught, the speed of the birds. Okay? Any questions about that term? All right. This next term is something that's also present in fluid mechanics. It's a pressure force. It just says you have put in some function of the density, and that's another thing you have to make some assumptions about. We basically just assume it's an analytic function of the density minus its mean value. So you have some local pressure, and all that means is that if I have high density over here and low density over here, there's going to be a force that tends to accelerate the system in that direction, just like there is in an ordinary fluid. The strange thing is this happens even in the VSEC algorithm, which you might think is strange because in the VSEC algorithm I didn't put in any repulsion between the particles. But that doesn't matter, and if you think back to your first statistical mechanics class, you'll realize why that doesn't matter. Even an ideal gas has a pressure. And if you take an ideal gas, the air in this room is an almost ideal gas, put it all on one side of the room and let it go, it won't stay that way. It'll spread out to be uniform, and you can think of that as being due to pressure forces. In that case, the pressure would just obey the ideal gas equation of state. But here I'm being more general and letting this equation of state be any analytic function I want. Yes? I'm sorry?
Is there a reason you chose a cubic damping and not a quadratic damping?
Just that I wanted to write something that was analytic in the velocity. But it's not crucial. I don't have to require that. What is crucial is that whatever I write down here is an analytic function of the velocity near, when the velocity is near the speed v naught. I assume that, and I assume that just because I don't think there's anything special about v naught. It just happens to be the speed the creatures pick. But you can put in pretty much anything you want that you can put in here that makes the creatures accelerate if they're going too slow, decelerate if they're going too fast, and leads to a unique steady state velocity will give you the same behavior. Yes?
In your pressure equation, is your average local or global?
Global. So it assumes there's some density the system wants to be at. Okay? What else do I have to say about these? These three terms all tend to make the velocity spatially uniform. You can see they're like diffusive terms. You can think of those as arising from the tendency to follow your neighbors. If you want to think about the fluid mechanics analog, these diffusion coefficients are like viscosities. Bigger diffusion coefficients means the thing is stickier. Okay? Things will decay more rapidly. And finally, we have a noise in here, a white noise that just represents the mistakes, and that white noise is zero mean and has as its sole parameter its mean squared amplitude, which I again take to be delta. Yes?
The constants in the first equation, can they also depend on the density?
Yeah, good point. Yes. Since we're being phenomenological, that is, it's a fancy way of saying since I'm just making these equations up, I'm not deriving them from anything, every parameter in these things can depend on any scalar quantity. So it can depend on the density, and it can depend on the magnitude of the velocity. That, as you might suspect, complicates the analysis of these equations a lot. But that's the assumption. Okay? So not only is the pressure a function of the density, but it's also a function of the speed, that is the magnitude of the velocity, and all of these other coefficients could also be functions of the magnitude of the velocity. Okay? What we assume, it's the usual rules in this sort of game, we assume that all those functions are analytic, and we expand them for small fluctuations about a uniform steady state. And that's how you get somewhere. And so your phenomenological parameters wind up being not these quantities, but the expansion coefficients in that. Yeah, go ahead. Mm-hmm. Yeah. So the assumption here is that the only thing aligning the creatures is their interactions with each other. Yeah. You could put in an aligning field, and I've actually done some work on that. Ultimately, the problem becomes much less interesting because they basically behave as they would if each of them was moving on their own and just responding to the wind. But if the wind is weak, then there's some interesting interplay between the ordering tendency of the wind and the ordering tendency of these terms, and I'm doing some work on that right now. Yeah. But here, what I want to get at is, if you don't tell the creatures which way to go, can they pick a direction themselves, even in the presence of this noise? And so we deliberately chose to focus on a case where there's no external fields. But it's easy to put an external field in. You just add a constant vector to this side. Yeah.
We have 3 diffusion constants.
Yes. So one of these diffusion constants, if you think about fluid mechanics, one of these diffusion constants, this one you can think of as the shear viscosity. So that's the one that will damp out motion where, say, you're moving slowly here and you're moving rapidly here. This one is a bulk diffusion constant. So this will damp out if you have a fluctuation where everything's converging in some region. This will damp that out. Okay? This one is a weird anisotropic diffusion constant that doesn't exist in an ordinary fluid, but does exist here. And it just reflects the fact that if you have a gradient in the velocity in the direction of motion, that's what this v dot grad represents, you might get different decay than if you have a gradient perpendicular to the direction of motion. Because after all, the system is not isotropic. Right? It can tell the difference between that direction and that direction. Okay. So I turned it off again. What am I? Wait. That turned on?
Just wait.
Just wait? Okay. All right. Yeah, amazing. Okay. So that's the hydrodynamic equations. Now, I want to emphasize something here. This is not a model of a flock. If you're considering a flock that obeys all the symmetries that I described, rotation invariance, local interactions, and no Galilean invariance, that is having a substrate, there's only 2 possibilities. These are either the equations. These will describe any flock that obeys all those criteria, or they're wrong. Okay? They've been out there for 20 years and no one's found a mistake in them yet, and microscopic derivations lead to these equations. So I think these are right. And they're general. Okay? They're general in exactly the same sense that no matter what fluid you're trying to describe, as long as it's a simple fluid, it's described by the Navier-Stokes equations. Okay? So it's not a model, it's the model. Okay? Or it's wrong. All right. Another way to say that, a slightly less egotistical way to say that, is that these equations are universal. That is, you can take the VSEC algorithm with repulsive interactions, you can add any bells and whistles you want, and all you will do is change the form of these constitutive equations and the values of these parameters. I'm sorry? Yeah, there's a lot of parameters, and it's actually even more than that when you start allowing for these functions to depend on density and velocity. So there's a lot of parameters in these equations, but the structure of these equations is completely determined by the symmetries and the conservation laws. Okay, that's the point. So any microscopic model you consider, if you do all the hard work of doing that calculation, in the end, you're going to be led to these equations. Now, if you care about the values of these parameters, and obviously for a lot of things you would, then you need to do those microscopic calculations. But if you care only about results that come from the structure of these equations, you don't have to do that. Okay, there was a question over here. Yeah. Mm-hmm. That's right. It's just whatever density the system in the absence of noise would settle down to spontaneously. Or, okay, in a lot of these simulations where you put the system in a box, the density is what you pick. You put a certain number of creatures in the box, and then this density is just that number divided by the volume of the box. Okay, but if you had a flock with a finite boundary, then it would spontaneously select some density, assuming that it had interactions that enabled it to stay together. Think about it, it's no different from what happens in fluid mechanics, right? If you make a liquid drop, if you make a drop of water here, it's going to spontaneously select the density of 1 gram per centimeter cubed. And if you wanted to calculate that, you'd be in for a lot of work. But if you just want to measure that and then say all the fluctuations in that drop in the density are small departures from 1 gram per cubic centimeter, then you could make this sort of approximation. That's all I'm doing. I don't think so. Even a dynamical system, you could imagine settling down to some steady state density, as long as it can stay together. I mean, that's the tough question, is can a flock surrounded by vacuum actually stay together? And that's a tough question, which I'm begging here. I'm assuming that somehow the system has spontaneously selected an optimal density, and that's either because we put it in a box or because it had some interactions itself that enabled it to do that. But I agree. It's an open question whether a flock can actually stay together or not. No pun intended. No, go ahead. Finish that. Well, the only way I know how to analyze these equations is to assume that there's some uniform steady state that I look at small fluctuations around. Okay? And if I do that, I find that there's a finite range of values of the parameters for which that state is stable. So that assumption, I guess what you can say is that assumption is internally consistent. Right? You can't prove that actually happens. You have to defer to experiment. But that's true of the Navier-Stokes equations too, right? When you formulate fluid mechanics, there's nothing that tells you that the water in here is actually a fluid. You have to do an experiment to see whether it is or it isn't. The experiments you do are based on seeing whether or not it obeys the Navier-Stokes equations, basically. Right? So our idea here is the same. We're assuming that a certain kind of state exists, a state of uniform density with small fluctuations around that, and uniform velocity with small fluctuations around that. We make predictions based on that assumption, and then you can compare those predictions with simulations or experiment. If they agree, then that's strong evidence that the state you have is actually a state like the one we're describing. Okay. So in other words, the game here is we're postulating a certain kind of state, making predictions about what the properties of that state are, and then telling experimentalists, go out and see if you see these properties. And if you do, then you're seeing our state. Okay. Sometimes you won't. Sometimes the water is frozen. Right. Okay. These are all good questions. Anybody else? I saw another hand up somewhere. Mm-hmm. Yeah, no, that's a good question. So if you have a given collection of organisms under a given set of local conditions, then these parameters should be the same for all of them. So they're independent of the size of the flock, provided the flock is very big. And remember, the flock has to be very big to even use these equations in the first place anyway. Okay, so the flock has to be big so the creatures don't see the boundary, because the boundary, of course, could affect their behavior. Right? Yeah, so that's a good point. If you change the conditions, then you'll change all these parameters. Right? But as long as you keep the local conditions fixed, as long as what any individual bird sees is kept the same, then all these parameters should be the same. So these parameters reflect everything we know about the psychology, the physiology, and the physics of the creatures. Or rather, they reflect all the things we don't know about it. All the things we don't know about those things are buried in these parameters. And if you change any of those things, you'll change these parameters. Okay? Yeah?
So do people actually mirror this parameters
I'm sad to confess, the only experiments where they've really been measured are numerical experiments. But yeah, you can measure them there. Basically what you do is you compare the behavior of the system to the predictions of this theory, and you pull out the parameters. And I'll show you some examples of that later. Okay, any other questions? All right, so, oh, no, I think you're right, actually. Am I supposed to finish at 10:30? Yeah. Okay, yeah, so I'll stop here. And so unfortunately, this means the coming attractions trailer is going to run over into the movie. But so I'll continue this next time. Okay, thanks. It's a good thing you said that. I would have gone on for another 3 hours. Yeah. Well, strangely enough, you actually need to include a noise if you want to study fluid mechanics, if you want to study thermal fluctuations. Okay. So it's not actually a unique feature of this model that we have noise. Even in equilibrium systems, people include a noise. You're not used to seeing that because in a lot of the applications in fluid mechanics, the thermal fluctuations are invisible. Right. If you want to describe the air in this room, you know, how the sound gets from my mouth to your ears, thermal fluctuations don't play a very big role in that. Although they play more of a role than you might think. The damping of that sound depends on the viscosity of the air, and the viscosity of the air is actually changed by the thermal fluctuations. So.
So in the equation we write down a viscous term, and the viscous term is temperature dependent, which in turn.
Well, but that's yeah, right. You can phenomenologically incorporate those effects of fluctuations that way. But if you really wanted to know, you know, suppose I shut up. Okay. Apparently, I've heard, and I don't know if this is true, and I've never actually done this simple arithmetic to figure out if this is true, but I've been told that someone with really, really acute hearing can sit in a silent room and hear a constant white noise. And that white noise is the thermal fluctuations in the air around them. Now, I don't know if that's true of human beings, but there's certainly machines that can detect that. And if you wanted to understand the spectrum and the amplitude of those fluctuations, the way you would do it is you'd take the Navier-Stokes equations and you'd add a noise. And you would make that noise obey the fluctuation dissipation theorem that relates it to the viscosity. And you can predict that. So this is, the noise is not the novel feature in these equations. Okay. The novel feature is having these Galilean invariance breaking terms and these convective terms at the same time. Exactly. And if you don't have the source term, see, I'm not studying